Honor and privilege for us to have Professor Hiraku Nakajima as one of the invited speaker in our John Conway Spirited Seminar Series. Professor Nakajima uh, is currently affiliated with and principal investigator at Kavli Institute for the Physics and Mathematics for the Universe at the University of Tokyo. And he has been awarded Geometry Prize from Mathematical Society of Japan, Geometry section, and then Spring Prize for Mathematical Society of Japan, then Coulomb Prize in Algebra by the American Mathematical Society, then a penalty of other long list of prizes he has already won, and one of the serious position he is holding at the moment is he's currently the president of elected member and president of the International Mathematical Union, and his research interests are in representation theory and geometry. And today he's going to discuss something which somehow lays a kind of foundation for the physicists who are particularly working in the area of string theory, standard model, and penalty of the related topic, which is a joint, I would say, joint area where mathematicians and physicists work together. And welcome, Professor Hiraku Nakajima, for and please proceed with your seminar.
Thank you very much for very kind introduction. So it's great honor for me to be invited to give this John Conway Spirited seminar. So unfortunately, I cannot go to Pakistan now, but in future I hope to be in person. Anyway, so this is based on my joint work with Coulomb and Finkelberg. So it's mathematical definition of the Coulomb branches of 3D and equal 4 supersymmetric gauge surface. So I start with some physical explanation of this gauge theory. So suppose we are given a compact Lie group and its representation of a quaternion. So if you are not familiar with the representation of a quaternion, then you can just consider the special case that so N is a usual complex representation of G, and then you consider N plus N star. So this is so basically the quaternion consists of 1, I, and J and K, and J acts on N star in a dual manner. So N plus N star becomes a representation quaternion. So I will not use the quaternion from now, so later on, so you can just assume that we are considering this kind of representation. Then for given group and representation, physicists associate the so-called supersymmetric gauge theory in 3 dimensions. And so it is also called N equal 4 supersymmetric gauge theory. So this N is the number of supersymmetry. So this is a technical part, and I will not use the detail of the supersymmetry. So you can just ignore up to this moment. And I will explain the crucial point, how supersymmetry plays a role later. So anyway, so this gauge theory is a quantum example of quantum field theory, so which is defined by the Feynman path integral. So you consider the space of all G connections A, and together with m-valued spinors phi on a 3-manifold X. Then you consider the Lagrangian S, A, and phi. And in fact, so I put the dot here. So this is the so-called super partner of A and phi. And as I said, I don't need the detail of supersymmetry, so I just suppress the super partner by dots. So the main layer is a connection and spinors. And then you integrate over by the measure. over the space of all fields. Okay, but it is famous that so this is infinite dimensional space, and there's no reasonable measure on that space, and this integral is not mathematically verified. For the usual path integrals, which was defined, which was used for quantum mechanics, that can be rigorously defined in some manner, but this is a three-dimensional space, and you consider the space of fields on three-dimensional space, so it's not very defined. But nevertheless, physicists have, because of the so-called supersymmetry, physicists reduce it to a finite dimensional usual integral and compute it in many examples. So this is a non-trivial step, and as I say, I emphasize again that I don't explain the detail of the supersymmetry, but this is the supersymmetry is the reason why this integral, infinite dimensional integral, is reduced to finite dimensional. So if you don't assume supersymmetry, you need to define Feynman integral over infinite dimensional space. No one succeeds to justify such integral. Okay. And for mathematicians, this suggests some interesting problem. So expectation is the following. So these integrals, so you can regard this finite dimensional integral. So this should give a topological invariance of three manifolds X. And after the so-called topological twist of supersymmetry. And this topological invariance includes Casson invariance, which has mathematical rigorous definition, and their generalization. So the mathematical approach to Casson invariance are completely different from this kind of approach. Integration over the space of fields. So if we can justify this kind of integral and this kind of physicist computation, it means that we have some new understanding of those topological invariants. So this seems to be big benefit for us. So if this is really achieved, if this expectation is achieved rigorously, then it seems we have very good understanding for topological. But I mean, this is at this moment it is too much to expect, unfortunately. So we have some approach. Maybe we only have partial result to that, but we consider some partial. We consider several approaches to this, to achieving this expectation. And even if we only get partial result, I think it's still interesting. Okay, so it is good to consider slight generalization of this Feynman integral. So we suppose three manifold X has bound. By the way, so here manifold is always C infinity manifold, not a complex manifold. So 3 is real three-dimensional. So X is a three manifold with boundary sigma. So sigma is a two-dimensional. And I don't say that this is oriented, but I always assume X is oriented. Then I first fix small a and small phi, which is a connection and the spinor on sigma, not X. And then we take the integral over the space A and large A and large phi, whose restriction to boundary is small a and small phi. And then I integrate in the same manner. So integral it gives some number, but here because the number depends on a and phi, so you can regard this is a function in a and phi. So in summary, so if you consider a Feynman integral over 3 manifold with boundary, then you get a function on the space of fields A and phi. Right? Then you introduce the so-called Cantor-Hilbert space. So this is the vector space of functions in A and phi. So this is very huge vector space if you consider it naively. Vector space. So A and phi is already, I mean, it's a connection with spinors. So you approximately, this is a space of functions on sigma. So this space of A and phi is already infinite dimensional. Infinite dimensional space. You consider the function space on infinite dimensional space. So you can consider L2 space on, for example, on finite dimensional space. So this is, of course, well-defined object, and the mathematicians study that. But here, A and phi, the space of A and phi is infinite dimensional space. You consider the function space on infinite dimensional space. So this is huge. Naively, this could be very huge space. But again, by the miracle of supersymmetry, these Cantor-Hilberts are expected to be much smaller space. I mean, in some situation, which is not in this context of Coulomb branch, but in other situation, so this Cantor-Hilbert space is expected to be finite dimensional space, for example. So this is much smaller. And quite often, this is the cohomology of finite dimensional subspace of A and phi. So S is usually called Lagrangian. So A and phi, small. Large A and, here I'm SUSY consider small and small phi. So A and phi satisfies equation motion, which is determined by this Lagrangian S. So then, so those A and phi which satisfy this Euler-Lagrange equation motion determined by S is a subset of all fields of A phi. So for example, if you consider the space of all functions, and if it satisfies the Laplacian equals 0, then it is a harmonic function, and harmonic function forms a finite dimensional space. I mean, it's usually one dimensional. So if you consider allow eigenvalues, then anyways, it's very much smaller, and you expect a similar thing. So this is one difference. So instead of all phi A and phi's, by this miracle of supersymmetry, you only need to consider those satisfying some partial differential equation, and you get finite dimensional subspace. And next, so instead of function on those spaces, function on the space, you replace it by cohomology. So if you know that the definition of the Coulomb cohomology, so Coulomb cohomology is defined by differential form, and differential form is a natural generalization of function. But the key point is that so Coulomb cohomology is defined by the operator D from P form to P. and kernel of D divided by the image. So by this process, instead of arbitrary differential form, you get much smaller space. And if you, so omega p is infinite dimensional space, but this Duran cohomology becomes finite dimensional. So we have, by these two processes, first we take a finite dimensional subspace, and we also take cohomology. So this quantum Hilbert space becomes much smaller than the space of function on infinite dimensional space. So you could expect it is reasonable hope that you can understand this quantum Hilbert space as a reasonable vector space. And this approach, this kind of thinking leads to an axiomatic approach to topological quantum field theory, which is due to Atian-Seeger. So for three manifold without a boundary, so this Feynman integral gives the number. So I assume this is a complex number, but in some situation it could be real number. So this is the case when there is no boundary. So this integral. And for two manifold, sigma 2, so it is natural to expect quantum Hilbert space is a reasonable vector space. And if you have a three manifold with boundary, then by this assignment, so g of x should be an element in this vector space. Okay. So Atian-Seeger proposed instead the following. So instead of considering the Feynman integral, which is not rigorously defined, so you just need to define those assignments, d of x3 and d of sigma 2, satisfying this condition. And also it is expected this satisfy the Green law. So if you have x divided into x1 and x2, and you have the boundary sigma, and so maybe one of the action is d of sigma 2 with opposite orientation is d of sigma, dual space of d of sigma. So then d of x is expected to be the pairing of z of d of x1 and d of x2. Right? So d of x1 gives element with the d of sigma, and d of x2 gives an element of the d of sigma with opposite orientation. So this is a dual, it gives an element in the dual space. Right? So you expect this quantum field theory, supersymmetric quantum field theory should give this kind of assignment. So this is a natural expectation. So then, as I said, instead of trying to define the Feynman integral directly, you should expect those assignments. You should expect to define those assignments. This seems more reasonable than the justification of the integral. But nevertheless, it is still not so easy. So I consider a very special case. So we just take most basic two manifold, which is two sphere. So we consider the quantum Hilbert space for two sphere. So this is a vector space. But in fact, it has more structures. So this is because the following consideration. So I draw this three manifold. So you consider the disk, three-dimensional disk, and you remove two smaller disks like this. So then X is a three-manifold, three-dimensional manifold with three boundaries. So you have outer S2 and you have two inner S2s. Then from the expectation which I just explained, so Z of X should give an element in Z of sigma, which is boundary. And maybe I forget to mention that. So Z of if you have disconnected surface and the corresponding quantum Hilbert space is Z of sigma 1, tensor with Z of sigma. This is one of the actions in topological quantum. And this is something natural because we are considering space of functions on the fields of sigma and sigma 2, sigma union sigma 2. But the fields on sigma 1 and the field on sigma 2 moves independently. So then the such function space will just become tensor. So anyway, you accept that. If you don't, if you are not, no, I think this is clear. So you just use this. Then Z of sigma, and also this is dual. Because the orientation is inner and outer, so this is the dual space of Z of S2 and one Z of S2. So you have this. So this, you regard this as home of Z of S2, tensor Z of S2 to Z of S2. So you regard this as a multiplication. So you take two elements from Z of S2 and then applying this formula to get a new element in Z of S2. So this you consider this as a multiplication. And you can check the associativity by drawing a picture. So associativity means that you put the same picture in here, but then somehow the associativity. So this picture is out. So yeah, maybe probably it's not so easy to explain by words. I think it is maybe you just draw a picture. And I hope you immediately see the associativity. And the commutativity is also clear because so there's no ordering between these two smaller disks. So you can the topological. Maybe I should also say. So in the original quantum field theory, it depends on the Riemannian metric, but because of supersymmetry and after the so-called topological twist, the resulted quantum field theory is independent of the choice of the Riemannian metric. So in particular, if you somehow if you try to if you change X continuously, then the result doesn't change. So in particular, you can exchange those two balls. So it means, so you have element here and here, so multiply. So you have A element here, B element here, but you can exchange them. So the order is irrelevant. It means that the multiplication is commutative. Then physicists consider the Coulomb branch of this quantum field theory as follows. So you consider this vector space Z of S2 and equip with this commutative algebra structure. So you get the commutative algebra. And then you take the spectrum. So this is a spectrum in the usual sense of in algebraic geometry. So this is a affine scheme, but in fact, you can show Z of S2 has various nice properties. And this is indeed in all examples. This is affine algebraic. But it also means that because this is a usual affine variable, Z of S2 is infinite dimensional vector space. So the affine algebraic variety is defined in affine space by polynomial equations. So vector space of polynomials is infinite dimensional. So in general, affine algebraic variety always has infinite dimensional coordinate ring. So Z of S2 is in particular infinite. This is somehow, so I said that, so this should be cohomology of finite dimensional subspace. But in fact, at the end, this is not quite correct. So it's because the space of field, because of the gauge theory, gauge theoretic origin. So you need to consider the space of all connections and spinor modulo gauge equivalence. So you consider the quotient space, and this quotient space has bad similarity. That is, I mean, or in technical term, it is called the stack. So it is by this reason, so this cohomology of the space becomes infinite dimensional in this situation. Although, as I said, this people expect this quantum Hilbert space is very small, but in this particular situation, it is infinite. But still, because this is affine algebraic variety, it's still reasonable vector space. So its spectrum is usual affine algebraic. Okay. And physicists even go further, or maybe this information, this definition comes first historically, and then this commutative algebra appears afterwards. So anyway, so this MCGM has a hyperkähler metric. So this is a Riemannian metric with some very specific property. So the solutions of Einstein's equation, for example. So anyway, so this, if you're not familiar with differential geometry, this is you just regard this as a very nice metric. And anyway, so I don't explain it further afterwards. And in fact, this hyperkähler structure is important only for the technical detail in the next more striking statement. So physicists say this original three-dimensional supersymmetric gauge theory in low energy limit, it is equivalent to another three-dimensional supersymmetric quantum field theory. So this is so-called sigma model. So with target space with this Coulomb. So sigma model is instead of connections and spinors. So this sigma model consider maps from three manifold to this target space. And so this sigma model is again quantum field theory. So this is defined in the same manner as before. So you have some Lagrangian. So I come back to this first page. So instead of A and phi, you integrate over the space of maps and for different S. So a priori, it looks, I mean, both are ill-defined, but it involves, so for Geyser, it involves A and phi connection and the spinors. But for sigma model, it involves this kind of maps. So this statement is very surprising. So two very different looking quantum field theory gives equivalent quantum field theory. So if you compute, so what do we mean low energy? So you compute, I mean, after topological twist, so you compute topological invariant in left-hand side, and you also topological invariant in the right-hand side. So as I said, it is still we are far away to justify those definition of topological invariance, but nevertheless, this statement predicts those two invariants defined left-hand side and defined by right-hand side are equal. So this is a very surprising statement. So this is a physical heuristic. Very difficult to justify, but still you can propose a concrete mathematical problem. So these two are easier problem. In fact, this is what I answered with Breber and Tinkerber. So give a mathematical justification of the above consideration. So namely, define Z of S2 as a commutative algebra. And it should somehow come from the physicist expectation. So namely, you should consider certain suitable subspace of A and phi and consider its cocoon. So realize this commutative algebra as a cocoon. And the multiplication is somehow reflects this should reflect the expectation. So this is the expectation. Okay. And so in fact, physicists already computed this Coulomb branch, MC of GM in many examples. So starting from work of Cyber Witten and Honda Witten and others. So they, in fact, they used the very sophisticated technique in quantum physics to determine the Coulomb branch. So as I said, this definition is somehow because involving the Feynman path integral. So even as I said, it becomes in many cases it becomes finite dimensional integral, but nevertheless it is still very difficult to analyze. But nevertheless, they have some very powerful tool to compute Coulomb branch in many examples. So I don't intend to explain their technique. Anyway, so it's not mathematically rigorous. But so maybe you heard about the so-called D-branes. So for mathematician, D-branes is something to do with the coherent sheaf-form algebraic varieties or derived objects in their categories. But physicists use a bit further, go a bit further than that, and they use some how to say. So anyway, so they, yeah, I don't want to go into the detail of this. They are problems. So anyway, so they have some technique to compute the Coulomb. So for given G and M, they say that MCGM is a sum space which is something explicit. So we need to check, in order to check that this definition is correct one, we need to check that this definition reproduce physics computation. So this is a consistency check for this definition, given in first one. And as I said, more challenging problem is this one. So in this definition, so you somehow, so you can consider the corresponding topological quantum field theory. But in this definition, somehow Z of S2, the quantum field velocity space is the coordinate ring of MCGM. This is more or less by definition. So this statement it becomes trivial. So what do I mean by justifying this is check this statement is trivial. So you go further, so you consider G of X 3 for closed and 0 without boundary and with boundary. Without. So this computation, this is the challenge. And the topological invariant from the right-hand side, G of S2 and G of X3, is what is called the Rosansky-Witten invariant. So Rosansky-Witten invariant has mathematical Degrassi definition. But unfortunately, this definition works only when the target space is compact and non-singular. As I will explain soon, the Coulomb branch MC of GM is always non-compact. I mean, this is a Affine algebraic variety, as I said. So this is always non-compact, and it often has singularities. So somehow one technical issue which we must solve in order to challenge this, to make sense of this problem, is to define generalized definition of Rosansky-Witten invariant to the case of non-compact and singular. I think this is already interesting enough, and it's somehow, I hope this is easier than this challenging problem, but this is the first problem which you need to solve before attacking this challenge. Okay. So any question or comment?
Probably toward the end. Okay.
Okay.
I may ask.
Okay, Hania. Go ahead.
Professor Nakajima, is this for this equivalence in star, this equivalence between two seemingly very different quantum field theories? Does this also relate to mirror symmetry somehow?
Mirror symmetry, it's some similar flavor with mirror symmetry, because mirror symmetry again is a statement about two sigma models with different target space. So X and X checks, so they are mirror to each other. But this equivalence is not a particular case of mirror symmetry. it has a similar flavor, but this is different.
Right. Thank you so much.
Okay, let me continue. So I explained the solution to these two questions. Easier ones. So due to my joint work with flavor mapping. So we should consider some space of fields on S2, but by technical reason, so we replace S2 by the following funny object. So which is somehow more easy to deal with in algebraic geometry. So we consider the formal power series, and we consider its spectrum. So this is a formal disk. So if you are not familiar, so you regard this as a very, very small disk. So this radius of this disk is very, very close to zero. And the star is a spectrum of formal Roland power series. So this is a complement of D. This is D minus origin. And then you consider 2D glued along the star. So this is a picture. So this has radius 0, approximately 0, but except that it somehow looks like S2. So this is the reason why we regard this space as analog of S2. And we consider the following space, R. So this is a modularized stack of the following objects. So P and S. So P is a principal algebraic bundle over this object, analog of S2. And S is the section of the associated bundle. So the value of this S is N. So this is a half of N. So M was N plus N star. And we consider that if you have a principal bundle, then you consider the associated vector bundle. And S is a section. So for more general coordinate vector space M, so this definition is generalized by those people recently, but this work is anyway, so is based on the following construction. So I just explained the special case when M is given in this form. So P and S is the analog, algebraic geometric analog of A and phi. So we consider maybe return back to here. So we should not consider arbitrary A and phi, but we should first pick up some finite dimensional subspace. So we consider, instead of connection A, we consider the principal bundle. So because it has algebraic structure, so it is not arbitrary connection. We consider something smaller. And more importantly, S is an algebraic section. So this satisfies the Cauchy-Riemann equation. So in that sense, this is smaller. And then we consider the cohomons. In fact, by technical reason, we consider the so-called Borel cohomons. This is slight variant. And then you define the so-called convolution product. So convolution product for functions, I think you are familiar with convolution product. So if you have function f and in x and y, and if you have function in y and z, then convolution product fg is a function in X and Z defined in this manner. So you integrate dy. So for the Fourier transform, you don't have a Z, and if you have a, fxy is a kernel of Fourier transform, and if you have a function g in y, then you get a new function which is a function in x. So this convolution is a slight generalization of this kind of integral transformation used in the definition of Fourier transform. Okay. So this notation is analog of this operation in the cohomology. So more concretely, so from this, you consider 3 disks glued along 2 punctual disks. Then you have 3 projections to this algebraic analog of S2. And if you have a cohomology class here, then you pull back to here and take product and then push forward to here. So it's analog of the operation like this. Analog of the operation. It's convolution product of function. Okay, then we show that this D of S2 with this convolution product is commutative. In fact, so this convolution product is typically not commutative, but somehow by a miracle of this situation, this becomes commutative. Otherwise, you cannot consider its spectrum. So you must show that this is commutative. And basically, this is the reason why we need to justify that this movement, the exchange of two disks in this setting. But it becomes commutative. And there are several properties. So first of all, so as I said, this is expected to be equipped with hyperkilometric. At this moment, it is difficult to justify that. But at least we can give the so-called holomorphic symplectic structure. And in fact, this is something more interesting. This is also something interesting. So this commutative ring is equipped with Poisson bracket from a deformation quantization of D of S2. So D of S2 has a deformation to a non-commutative ring. So if you have F and G in D of S2, then you lift to non-commutative algebra and then take commutator. And so H bar is a non-commutative parameter. So F, because the product is commutative at H bar equals 0, so this is divisible by H bar, and then take limit. You first divide by H bar and take the limit. So this is the definition of Poisson bracket. And this Poisson bracket is coming from a symplectic form on this MCG. And also, this is very nice Poisson variety or symplectic variety. So it is equipped with integrable system. So MCGM as a map to vector space. This is vector space. So because we define the Coulomb branch by cohomology of some space, so it is equipped with cohomology or equivalent cohomology. So this is H star of point divided quotient stock. So because we are considering quotient space, as I explained, then so you have the natural morphism to this equivalent spectrum of equivalent homology. And it is classically well known that this equivalent spectrum of this equivalent homology is a vector space. And this small L is the rank of the group. And this is the quotient of the Lie algebra of the maximal torus complexification G divided by Y. And these components of this is a Poisson committee. So in that sense, this is the integrable system. So in some sense, I mean, Poisson geometry of symplectic geometry of MCGM is something very interesting. Yeah, because the time almost up, so I maybe skip the third statement and give some example. For example, so if G is U1 and M equals 0, so in this case, you must understand, so there's no spinors. And G equal U1 means that you are considering the line band over this strange algebraic geometric analog of S2, and you compute the homology. So this is some computation you must do, but at the end you find that MC is just R3 cross S1, or maybe algebraic geometry, this is C plus system. So the coordinate ring is C of X plus minus and Y. So this is some not so interesting space, but if you consider the non-Arpedian group, then you get some interesting space. So for SP2 or SU2, so you get the so-called Atiyah-Hitchin manifold. So this appears in differential geometry. So this is a modular space of SU2 monopole on RC. So anyway, so the Atiyah-Hitchin studied this space. And if you slightly change the group from SU2 to SO3, SO3 is a quotient of SU2 by D2. Then the relation is opposite. So here you have the coupling. So MC is double kappa of this Atiyah-Hitchin. So in general, you consider the fundamental group of the group G. So this is for these two examples, this is a finite group. So SP3 is simply connected. This is trivial, but SO3 is as fundamental group G2. And you take the Pontryagin dual. So that's the reason why it goes in the opposite here. So Pontryagin dual acts on the Coulomb. And this Pontryagin dual of the fundamental group appears because so we are considering the principal G band over the analog of S2, algebraic analog of S2. So this topological type of this principal G band is classified by fundamental group of G. So this is the reason why we have Pontryagin. So maybe I must finish. Maybe this is the final one. So there's the so-called quiver gauge theory. So this is a very particular choice of G and N. And as I said, the original motivation of this study was to consider the topological invariant for three manifolds. But it is also interesting in geometric representation theory. So you start with this particular choice of G and N, something from quiver. then this Coulomb branch is expected to be related to representation theory of Katsumudi reality. So this is something which we didn't expect initially, but somehow this suggests that even ignoring this three manifold topological invariance, the Coulomb branch itself seems to be very interesting space to explore. So in particular, it might have application to representation. Okay, now I stop here. Thank you for attention.
Thank you very much, Professor Nakajima. Any questions from the audience before? Yeah, Hania, do you have any?
Sure. I was just curious. You mentioned the Casson variant. So is it easy to? Well, I mean, is it straightforward to just say what the implications of this are?
So are you familiar with equivalent homology? So
Yes.
on this disk, you have the S1 action. So just rotating the disk. So it acts on all the space. So in particular, you can also equip S1 action on R. So then you can consider S1 equivalent homology. So this is an algebra of equivalent homology of point. So this is a polynomial ring in one variable.
Mm-hmm.
And then, so this S1 action is counterpart in this original intuition for this G of S2. So here, if you just consider topological as a topological manifold, so we exchange two disks. So there is no S1 symmetry in here. But instead, we consider the following picture. This is larger disk, and we consider the axis like this, and we consider the S1 action just rotating like this. Then, if we consider this S1 action, then you cannot put arbitrary, you cannot remove arbitrary small disks. But you can still remove the following one. So if these two small disks also pass through this axis, then this whole picture has S1 symmetry. Now, but because this S2 can move only vertically, so there's ordering in bottom disk and upper disk. So recall that I explained the commutativity of the multiplication is coming from the exchange of two disks.
Right.
But if you just consider this picture, there is no longer, we cannot no longer allow to exchange two disks. So this is the reason why once you consider this picture, you lose the commutativity. And indeed, once you equip this function, then this algebra, convolution product is defined in the same way. But algebra is not commutative. So this is a non-commutative deformation. And once you have the commutative algebra with deformation to non-commutative algebra, then you can define Poisson algebra, Poisson product, Poisson brackets in the same in this format. The point is that somehow, in order to understand the symplectic geometry of this variety, it is also natural to understand the representation theory of this algebra, this non-commutative algebra. Somehow, this is what is called the deformation quantization of this commutative algebra or this variety. So geometry of this, symplectic geometry of this variety is somehow deeply connected to this representation theory of this non-commutative algebra. So we have lots of examples. Of such non-commutative deformation, and this framework gives lots of examples of such non-commutative deformation. This is what I want to say.
Right. Thank you so much.
Thank you. Professor Hiraku, I have a question. Why do we assume the formal power series instead of the usual symmetric polynomial ring?
You mean in the definition of this?
When we were discussing about spec
This one?
of, maybe here, yeah.
Yeah, we just use use. Yeah, one reason is somehow, I mean, so I explained by topological quantum field theory, but somehow and one heuristic explanation is that in this picture, so those two disks should be very small. So compared with larger disk, these two disks should be very small. And so this formal disk means the disk is very small. So in topological quantum field theory, there is no meaning of the size, but because of the intuition, the disk should be very small. Maybe let me try to give another explanation.
You want to keep the ring as local? That was the reason?
No. That is somehow here you should not confuse this technical part and the resulted the commutative ring. This is not the formula at all. So this is the usual polynomial ring.
Yeah,
and
here.
The spectrum is a usual variety, not the neighborhood point. But this is we first consider the modular space, and then take the cohomology. And for modular space, somehow we need to consider that those connection fields are defined in a very small region.
Okay.
Yeah, maybe. So this is another picture. So we have sigma, and we have two small disks that we remove. So m equals sigma times interval minus disk. So dm is 2 copies of sigma, and that's 2. So this gives d of sigma tensor g of S2 to d of sigma. So in particular, by this construction, d of sigma is a module over d of S2. So this is another topological construction. And somehow we somehow how to say we expect this multiplication by z of s to appear multiplication. So multiplication z of s2 occurs very small region in sigma. So this is somehow physical intuition. So that is the reason why this z of s2 is very small, should be very small. Yeah, maybe it's or maybe you can just regard this is a technical reason, and we.
Okay.
Yeah.
Okay. And one more question. In the beginning, you was talking about the Feynman integral, and you said that this is an open problem to find the topological invariants for that integral. So, may I know which kind of topological invariant has been known up till now?
So even for Castle invariant is the case when G is SU2, SP2, SU2, and M is equal to 0. So this is what I mentioned that the corresponding Coulomb branch is at a Hitchin manifold. And in this case, I mean, Castle invariant is defined. Castle originally defined for rational, defined over integral homogeneous sphere, and that was generated to arbitrary Riemann by Walker and Lesko. But anyway, so the left-hand side is well defined, at least for closed Riemann manifold. But the generalization to arbitrary Riemann manifold with boundary is still open. And on the other hand, for right-hand side, so as I said, the X is non-compact. So at this moment, the definition of Rosansky-Witten invariant is mathematically rigorous only for compact hyperkähler. So at the Hitchin's manifold is non-compact.
So just out of my curiosity, is there any benefit of discussing the same problem in projective setting?
Projective setting. What do you mean by projective setting?
So because you are considering the affine structure associated to these manifold. So again, compactification to taking and considering the algebra associated to the projective algebra, projective spaces.
Yeah, I think I mean, for example, I mean, somebody asked about the Miller symmetry. So Miller symmetry can be regarded as follows. So you basically usually people start with pairs of Calabi-Yau manifold X and X check, which is usually compact. But you can regard as follows. So you suppose you only know X, and you try to consider X check as a some result of some construction, like which I explained here. So in Miller symmetry, so people usually state the Coulomb-Witten invariant of X is computed by the period integral of X check. So it roughly means that complex structure of X check can be constructed from Coulomb-Witten invariance of X, right?
Yeah.
but the period integral is the only part of information. And if you try, I mean, anyway, so you have this kind of difficult problem. So construct X check flow. How to say? Construct X check from Gromfit invariant of X. So you somehow need, and also the Fukaya category of X check is somehow understood from coherent shift of X. This is the homological mirror symmetry. So it means that you construct X check, Fukaya category of X check. So that is somehow you regard this as a construction of X check. So from the coherent shift of X. So in that sense, mirror symmetry has very similar flavor with this one. But in this particular case, particular construction which I explained today, this is much I think much easier than the construction of mirror manifold from X. Mirror manifold X check.
Okay. Thank you. Is there any other question from the audience? Okay, if this is the case, let us thank the speaker, Professor Hiraku Nakajima. Thank you very much for accepting our invitation and delivering this talk. Definitely, it was loaded with a lot of technical stuff for the students, but definitely it contains many important questions what anyone can consider. So for further research and inquiry, and please feel free to write Professor Nakajima if somebody would be bearing some question and probably need more time to grind it. So once again, thank you very much, Professor Hiraku, and definitely we will invite you sometime in Pakistan, and definitely would love to have you here. Would love to have you here. Yeah. Thank you very much. Thank you, everyone. Bye bye. Take care.
Bye.